Hello, yeah, in this video we start a series machine learning using R. And in this video we want to talk about how to perform linear regression analysis. Linear regression is a supervised learning algorithm that models the relationship between variables with a straight line. So as we say, machine learning can be classified as supervised learning, unsupervised learning, or semi-supervised learning. Supervised learning meaning in our training data, we have the value for the dependent variable. Okay, so they're already known. Okay, it predicts outcomes by fitting the best line using the least square method. And also the model is simple, fast, and easy to interpret for linear trends. It assumes errors are independent, variance is constant, and the relationship is linear. So these are the three basic assumptions for linear regression. And linear regressions are used broadly for predictions and understanding variable influence. So they can be predictive models and they can be explanatory models. Okay. And so here is I want to make a complaint is a statistician that machine learning community steals ideas from statistics. Okay, so linear regression is a statistic method, and you can find a very comprehensive, very detailed information about linear regression analysis in almost any statistics textbook. Okay, so here I'm not going to spend too much time to go into details about linear regression, but rather just show you a quick example of how to run linear regression analysis. So let us set up the random seed. We create a continuous predictor using normal distribution. We create a categorical predictor with three levels, group 1, group 2, and group 3. And then we need to define coefficient because we're generating a synthetic data. So we define the beta regression parameters. We also call the facts. So beta 0 is 5, beta 1 is 2. And since we have a three-level categorical predictor, we define beta 2 as C, 0, 3, and negative 2 as effects for categorical levels. Group 1 is the baseline. And we need to add an error term. So epsilon is another normal random variable. And then in order to assign numerical values, to compute the dependent variable y, we have to make the categorical variable, which has a value group 1, group 2, group 3, as the numerical value. Okay, so we just use the ES numeric. Now it turns into 1, 2, 3. Okay, and now we create a response variable y with categorical effect using beta 2 as the user-defined parameterization. Okay, so it's a little bit complicated when you have a categorical variable. So you have to do parameterization, and you have sometimes you call it dummy coding. So here you can see it's a y assigned as beta 0 plus beta 1 times x1 plus beta 2. Then you don't have anything in there. Then bracket x2 underscore numerical, then plus epsilon. So the middle term, like beta 2 x2 underscore numeric, that's the operator that you assign different numerical values for in the beta 2 based on the levels like 1, 2, 3 in x2 numerical. Okay, so we do that, and now we put everything together as a data frame. This is what it look like. So y is the dependent variable, it's continuous, and x1 is continuous predictor, x2 is a categorical predictor. And then we can simply just run model as the output from LM, that's linear model, y tiered x1 plus x2, data equal to data. So here, when we created x2, we already defined it as a character, as a factor. So we don't have to do anything. We just put x2 in the equation. But if x2 is, say, a numerical vector, then you can use s dot factor in front of x2 to make it a factor as a categorical predictor. Okay? And then you can, using the summary function to print out the results of the linear regression, you can see it has a model call, give you the formula, give you residuals. So this residuals are a little bit large, the maximum of 16, the minimum of negative 11. But then you have the coefficient, show you the estimate of the beta, the regression parameters, then errors, t-values, and the probability. But the p-values and marked with the star system. So here, for example, you have most of them are significant at the level, say 1 star 0.05. Okay. And I think that X1 is highly significant. Okay. So this is kind of the output, look what it look like. And then you have the residual standard errors, and you have the R square, adjusted R square, and the F statistics and its degree of freedom. Okay. And then p-value, that's the overall model for the like yeah, I think just showing you whether fitting this model is better than fitting the intercept only. Okay, so it does. Okay, so there are many more things you can do with this linear regression, and you can check out my videos on, for example, model diagnostics, including residual analysis, how to assess a good model fit, and also how to assess influential data points such as outliers. Okay. So it's a very rich topic, and linear models is kind of the starting point for all regression models. I have another video focusing on like a diagram with multiple linear regression in the center and branch out to all kinds of different regression models when we want to dealing with violations of the basic assumptions of multiple linear regression. Okay, I'll stop here, and thanks for watching, and please like our video, click on notification, and subscribe to our learning channel. Thank you.